Before the invention of photography, the only way for us to process the information of the stars was to look at it and do our best to draw what we saw. Well, now that photography comes into the picture, that's our gateway to our modern astronomy. It started off with having these photographic plates, which would need these long exposures in order to absorb the information. It's expensive, slow, but it is the footstep to the devices that we use now, like our charged coupled devices. Basically, any electronic detectors, any device that will take a stray photon, boom, and turn that into an electrical signal. That's how our modern photography works today, and gives us the ability to take amazing pictures of the skies. So a charged coupled device, also known as a CCD, works on the principle of having a grid of different pixels, and when a photon comes in and hits that grid, say a red photon hits this pixel here, well, that determines a electrical signal that will go down into the device and sent to the remainder of your electronics to process. So each pixel will receive a photon that will change a certain amount of current, move a certain amount of current through this CCD. And that current can be processed out here. The output amplifier just goes to other electronics to say, hey, what type of photon, what wavelength hit this pixel here? And so the idea here is that you have photons exciting different pixels, different little tiny plates, and then convert that into this nice, clean digital signal. So advantages of a pixel version, this digitized version of photography, instead of having a plate, is that, well, the smaller you get these pictures, these pixels, the smaller you get the pixels, the more information you can store there. Whereas the old analog methods, it's kind of just this sheet that you just hopefully all fills out correctly. Here you have very fine precision control of the images that you will capture. Now say you're less interested in getting a picture, but you want to see the spectrum. You want to see, well, what's the composition out there? Well, simple. You just use a spectrograph, right? We've seen concepts like this in previous sections. You'll send the light in, right? This lens here just collimates. It makes it so that all the lights come in nice straight patterns. And then you'll use your optics. Here it's a triangular prism to split up the colors and get yourself a red, green, violet spectrum here. So you can specify the dimensions. What's the size of these lenses here to focus out what type of light you want to study that you're hoping to find. So you build your spectrograph to split the light up, find the wavelengths that you're looking to find, and then record them on a nice CCD for later analysis. Everything we've discussed so far has had as an inherent assumption that you're looking at colors in the range that we can see. We always are this bias of thinking of the visible spectrum. But remember, the visible spectrum is just a tiny fraction of the entire electromagnetic spectrum. So we need to ask ourselves, what light can reach us here on Earth? What's the purpose of having satellites in space? The goal is not to have a satellite in space to get closer to the stars. It's a trivial distance going from the surface of Earth to an orbit around the Earth. It's just not a significant enough change to matter. But by putting satellites above the atmosphere, high in orbit around the Earth, you can see other types of photons, other wavelengths of light that aren't reaching us on our ground-based telescopes. Let's go to this chart. All right. We'll ask ourselves, hey, take a type of light and ask, does it get through our atmosphere? And you look at radio waves, yes. You'll often see radio telescopes. They are ground-based telescopes because radio waves are these long, lazy ones that are really good at getting through Earth's atmosphere and reaching us down here on the surface of the planet. Now the microwaves, nah, those get blocked by our atmosphere. Infrared, a little bit passes through. Visible spectrum of light, this range of photons, those are really good at getting through our atmosphere down to this planet. It's why our biology evolved to detect these range of colors. Now anything above that, once you start getting into the ultraviolet ranges, UV and above, those tend to just hit our atmospheres, immediately absorbed, just impact, and none of that will really penetrate down here to Earth. So we don't have to worry about being bombarded by X-rays or, heaven forbid, gamma rays getting down to us on the surface of the Earth, because our thick atmosphere will get bombarded by those first, and those photons at this spectrum, this range, just can't penetrate the atmosphere and reach us. But there's a lot of interesting information stored in the ultraviolet X-rays and gamma rays out in the universe. So we'll send satellites into space, satellites that are sensitive to these types of photons, to help us capture the light that's out there that we're not seeing here on Earth. Here's another picture representing how much these photons will penetrate down to the Earth through our atmosphere. So the radio waves, those do a great job of getting down to us, hitting what we call the radio window, just the range of radio wavelengths that are coming from the cosmos and reaching us down here on Earth. The microwaves tend to get cut off. Infrared a little bit can get through. And then we get to what some will call the optical window, just the visible range of photons that get down to us here on Earth. Now keep going up the spectrum, and you see, well, how far into the atmosphere do these photons penetrate? Ultraviolets do get down to us. Right? If you ever want to get a suntan, or for some people a burn, you're looking for those UV rays. All right? The X-rays, those don't do a great job getting past our thermosphere. But some of the shorter wavelengths, they can penetrate a little further due to complex interactions that we won't get into today. But some of them will get down to our mesosphere, but nothing in these higher ranges starts going through the stratosphere, and that's about the region that you'll see airplanes flying around 10 kilometers above the Earth's surface. So the point is that look at the spectrum of light that you want to study. Are you looking at gamma rays? Do you want to study ultraviolet? Do you want to study microwaves? When you're designing your experiment, designing a camera to try and picture the universe, you need to choose the correct instrument based on what wavelength of light you want to study. We'll keep our focus on our ground-based telescopes for now, and we'll talk about radios. How do the radio telescopes work? Well, think of it this way. You can have a radio wave that's coming in from here. It will hit the dish, and the parabolic nature of it will then focus the light back there to the actual detector. And that's what all these dishes are for. Take a radio wave comes in, hits the dish, and the geometry sends all these radio waves back towards that detector right there. So obviously these radio telescopes allow us to see things in that radio spectrum of light. These will be wavelengths of about a centimeter to 10 meters is what we'll focus on. And the reason we want to study these is because radio waves, they do a great job of passing through gas. There's a lot of dust in the universe, a lot of stray gases out there between us and the stars. So any of the radio waves, any light that can get through it, are prime examples of things we want to study, because that will contain the information that we want to find. Now recall we just said that some of the radio waves we want to study can have wavelengths on the order of 10 meters. Well, these dishes aren't big enough, so how are you going to study all of these large wavelength radio waves? You do what's called an interferometric array. Every single one of these are actually part of a cluster. In some sense, we could say this whole thing is one big telescope, designated to try and observe all the radio waves and use interferometry to add the signals back up to get the original source signal. Instead of having telescopes, we can also finally talk about spacecraft as our last option of our optical measurements of the universe. Well, the goal of a spacecraft is to launch it off, get it outside of Earth's orbit, and try to get to fly by your target destination. Say, for example, this artistic rendering of Cassini doing a flyby of Saturn. And as it's flying by, take as many pictures as you can. Now you've gotten the distance equation out of the picture. You're a very close object. Try and get as many pictures as you can and send those pictures back to us here on Earth to study that information in more detail. Other things we've launched out there, things like Voyager 1 and Voyager 2, whose purposes were to do what are called flyby missions. All right, fly out there, zoom by, get as many pictures. Orbiters, well, those are designed to fly towards the planet and then get trapped in the gravitational well and try and just keep orbiting that planet and take as many pictures as you can. Now, at the end of our optical spectrum, we'll eventually start to shift towards our non-optical tools. That'll be our next video. And that's when we'll talk about things like the Randers, rovers, atmospheric probes. These are things that are trying to pull insight not just from pictures, from photography.